In this video, we're going to talk about calculus as it relates to position, velocity, and acceleration. Perhaps you're wondering, how do I know when the particle is moving to the right or moving to the left, or when it's at rest, when it's speeding up, slowing down, and things like that? So we're going to focus on almost all the questions that are related to position, velocity, acceleration. So in calculus, most textbooks would say that S of t represents the position function. The position basically tells you your location. It can tell you the location on the x-axis or on the y-axis or even in an xy coordinate system. Using the position function, you can find distance and displacement. So for example, let's say if we have a number line. If you start from the origin, so let's say the position is 0 on the x-axis, and let's say you travel 4 meters to the right. Your new position is 4. Now let's say if you travel 7 meters to the left, 4 minus 7 is -3. So your final position is -3. Now sometimes you might get a question like, what is the total distance that the object travels? The total distance is simply the sum of the two numbers. It's 4 plus 7, which is 11. Distance is scalar. Direction does not apply for distance, so distance is always positive. Now for displacement, it can be positive or negative. In the first part, the displacement is +4. For the second part, the displacement is -7. So the total displacement is 4 plus -7, which is -3. So if you look at the net displacement, we started at position 0 and we ended at -3. So we went 3 meters to the left. So that's why the net displacement is -3. But for a typical calculus problem, whenever you want to find total distance, you're going to get these two numbers. One is going to be positive, one is going to be negative if it changes direction. Just make each number positive and add them. That's going to give you the total distance. But to find total displacement, if you get these two numbers, add them the way it is without changing the negative sign. So +4 plus -7 will give you -3. You can also find displacement by taking the final position minus the initial position. Let's say A is the initial time, B is the final time. So it's simply the difference in 2 points. Now what about velocity? How can we find that? Velocity, which is associated with speed, is distance, or rather displacement divided by time. Speed is the distance divided by time. Let's be more specific. If you want to find average velocity is equal to the net displacement divided by total time. Average speed is the total distance divided by total time. So velocity is a vector, the same way displacement is a vector. Velocity and displacement depends on direction. So if you're moving to the right, the velocity and the displacement will be positive. If you're moving to the left, velocity and displacement is negative. Speed and distance are always positive. Now you can find average velocity by taking the displacement, which is the final position minus the initial position divided by the change in time. That's the time at B minus the time at A, or simply B minus A. So the average velocity is basically the slope of the displacement function, particularly the slope of the secant line. You can find average speed the same way. But just remember, if you're looking for average speed, it's always positive, it's never negative. In addition, make sure you know that the average velocity is the same as the average rate of change of the position function. the instantaneous rate of change of the position function is the same as the instantaneous velocity. So to find the instantaneous velocity, which is a function, its velocity at some time t, it's equal to the first derivative of the position function. So if you want to find the instantaneous velocity at 2, find the derivative of the position function and then plug in 2. Now the instantaneous velocity is the same as the slope of the tangent line for the position graph. So let's say if we plot s of t with respect to time, and let's say we get a curve that looks like this. The average rate of change, or the average velocity, is the slope between 2 points. It's the slope of the secant line. A secant line is a line that touches the curve at 2 points. Now the instantaneous velocity, or the instantaneous rate of change, is the slope of the tangent line. A tangent line is a line that touches the curve at 1 point. Now sometimes you can use the slope of the secant line to approximate the slope of the tangent line. If this point is in between these 2 points, if it's the midpoint, the slope of the secant line becomes a good approximation for the slope of the tangent line. And as these 2 points, as they move closer to the point of tangency, they will be even more accurate. So you can approximate the slope of the tangent line using the slope of the secant line as the change in time approaches 0. Now, it's important for you to understand this because sometimes you might be given a data table instead of the position function, and you won't be able to find the first derivative and plug in some value of t to get the instantaneous velocity. Sometimes you need to find the slope of the secant line, or the average velocity, to approximate the instantaneous velocity. So if you're given a data table, that's the only way you could find the instantaneous velocity. You can only estimate it rather than getting an exact value. So we said the slope of the tangent line is approximately equal to the slope of the secant line if delta t approaches 0. Now the slope of the secant line is basically the average rate of change, and the slope of the tangent line is the velocity. Now the average rate of change, we said it's s of b minus s of a over b minus a, but let's use t. Let's say b is time at point at b, and a is just the time at a. So we get this function. So the change in position divided by the change in time equals the average velocity. But as the change in time gets very small, as it approaches 0, it becomes the instantaneous velocity. So we could say v of t is equal to the limit as delta t approaches 0 for this function s of b minus s of a over, we'll call this the change in time, delta t. Now notice that this formula is similar to the definition of the derivative formula. F prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x divided by h. Some textbooks will use delta x instead of h, but it's the same thing. But notice that the original function is the position function. The derivative of the position function is velocity. Notice the similarities between the two equations. S of a is basically the original part of the function, and this is s of b, which corresponds to this part of the function. Now, this equation also looks similar to the alternative form of the derivative. F prime of a is equal to the limit as x approaches a for f of x minus f of a over x minus a. So as x approaches a, x minus a approaches 0. Let's say if a is 3. As x approaches 3, it's going to be like 3 minus 3, which is very close to 0. It's not exactly 3, but it gets very close to 3. But either case, it's for you to approximate the instantaneous rate of change, the denominator has to be very close to 0. Not exactly 0 because it will be undefined, but once it's close to 0, you can get the slope of the tangent line, which is the instantaneous velocity. But now let's move on. Enough of that. So how do you know when a particle is moving to the right and when it's moving to the left and when it's at rest? Whenever a particle is moving to the right, the velocity is positive. It's moving to the left when the velocity is negative. And the particle is at rest whenever the velocity is 0. Now, you have to be careful. When the velocity is 0, it doesn't mean that it's like completely at rest, so to speak. Because sometimes the object could be at rest and not moving, and it's staying at rest. The velocity is 0. Other times, the object can be moving to the right, and then it changes direction. As it changes direction, it's at rest for a very, very short time. So whenever velocity is 0, it could be at rest, or it could be changing direction. So if you have an object that's just at rest, not moving, and staying there at a long time, it's not changing direction, but it's at rest. Other times, it can go from moving to the right to the left. It's going to be at rest temporarily, so watch out for those two situations. If it's at rest or if it's changing direction, v is 0. Now, let's say if acceleration is positive. What can you tell me about the velocity? Whenever acceleration is positive, the velocity is increasing. And when the acceleration is 0, the velocity is constant, which means that the speed will also be constant too. If the acceleration is negative, velocity is decreasing. Now keep in mind, instantaneous speed is the absolute value of instantaneous velocity. So if the instantaneous velocity is -5, the instantaneous speed is +5. If the instantaneous velocity is +8, the instantaneous speed is +8. Velocity is speed with direction. Now, how do we know when a particle is speeding up and when it's slowing down? A particle is speeding up when the acceleration and the velocity have the same sign. So if the acceleration is positive and if the velocity is positive, it's speeding up. Or if the acceleration is negative and if the velocity is negative, it's also speeding up. Now an object will be slowing down if the acceleration and velocity have opposite sides. So let's say if the acceleration is positive and the velocity is negative, or if the acceleration is negative and the velocity is positive, the object will be slowing down. Now let's make a table. So we're going to have velocity, acceleration, and for the next one, it's going to be moving to the right, to the left, or at rest. And then if it's speeding up or slowing down. And the last one, if velocity is increasing or decreasing. So let's say if velocity and acceleration are both positive. And let's say if it's positive, negative, negative, positive, or negative, negative. So for the first one, is it moving to the right or to the left? Whenever velocity is positive, the object is moving to the right. And when it's negative, it's going to be moving to the left. Now what about speed? For the first one, is it speeding up or slowing down? So whenever velocity and acceleration have the same sign, it's going to be speeding up. whenever they have opposite signs, it's going to be slowing down. Now what about velocity? When is velocity increasing and when it's decreasing? Velocity is increasing whenever acceleration is positive, and it's decreasing whenever the acceleration is negative. Now I have some more questions for you regarding this table. Go ahead and fill it in if velocity is positive and if acceleration is zero, or if they're both zero, or if velocity is zero and acceleration is positive, or if velocity is zero and if acceleration is negative. So the object is moving to the right if velocity is positive. But whenever velocity is zero, the object is at rest. Now let's focus on the at rest part. What is the difference between the velocity and acceleration both being zero compared to when the velocity is zero but the acceleration is positive? What is the particle doing under these circumstances? When velocity and acceleration is zero, the object is at rest and it's staying at rest. It's just going to stay there. It's going to sit there. Now, what about if the velocity is zero and the acceleration is positive? It can mean one of two things. The object is temporarily at rest and it's about to move. Now, if it's accelerating from rest, it's going to move to the right. Or, if it was previously moving to the left, it's changing direction as it moves to the right. So I'm going to put an arrow, meaning that it's about to move to the right. Now, if velocity is zero and acceleration is negative, it could be accelerating from rest but towards the left, or previously it could be moving to the right and then changing direction going to the left. Either case, it's about to move to the left. Now, what about speed? Whenever acceleration is zero, the speed is constant. Now, the same is true for velocity. If acceleration is zero, velocity and speed are both constant. Now, what about if velocity is zero and acceleration is positive? Is it speeding up or slowing down? We know if velocity and acceleration have opposite signs, it's speeding up. But what sign is zero? It's not positive, it's not negative. So we can't really use zero to help us. Now, keep in mind, think about where the particle is about to move. It's about to move to the right. So even though the velocity is instantaneously zero, it's about to be positive. So let's put 0 plus. Since it's about to be positive, these two signs are the same, so it's about to speed up. Now, when acceleration is negative and velocity is currently zero, it's going to move to the left. It's about to move to the left. And as it moves to the left, velocity is negative, acceleration is negative. And so it's going to be speeding up since these two signs are the same. So in both cases, it speeds up. Now, whenever acceleration is positive, the velocity is increasing. And whenever acceleration is negative, the velocity is decreasing. So hopefully this chart can help you to identify when a particle is moving to the right, when it's moving to the left, when it's speeding up, slowing down, and things like that. Now let's work on an actual example. So let's say the position function with respect to time is t to the third minus 6t squared plus 9t plus 1. So here's the first question. go ahead and find the instantaneous velocity. Find the velocity as a function of time. And let's say the position function is restricted for the first 5 seconds. So what is v of t? V of t is the derivative of the position function. Now, you need to be familiar with the power rule. The derivative of x to the n is simply n times x raised to the n minus 1. So the derivative of x to the fourth is 4x cubed. The derivative of x to the fifth is 5x to the fourth. And for x to the sixth, it's 6x to the fifth power. The derivative of a number in front of x, like 5x, is 5. Negative 3x is negative 3. 4x is 4. Finally, the derivative of any constant like 7 is 0. The derivative of 5 is 0. Now let's find the derivative of the position function so we could find the velocity function. The derivative of t to the third using the power rule is going to be 3t squared. The derivative of t squared is 2t to the first power. And the derivative of t is simply 1. And as we mentioned before, the derivative of any constant is 0. So the velocity function is 3t squared minus 12t plus 9. So that's what you can do to find the instantaneous velocity as a function. Now, how can we find the average velocity, let's say on the interval 1 to 3? What would you do to find the average velocity between t equals 1 and t equals 3? To find the average velocity, it's going to be the displacement, which is the change in position, s of b minus s of a, divided by the change in time, or b minus a, where a is 1, b is 3. So we got to find s of 3 minus s of 1 divided by 3 minus 1. So if we plug in 3 into the original equation, what are we going to get? So it's going to be 3 to the third power minus 6 times 3 squared plus 9 times 3 plus 1. So all of that is s of 3 and then minus s of 1, which is going to be 1 to the third power, which is 1, minus 6 times 1 squared, that's 6, plus 9 times 1, plus 1. And all of this is divided by 2, which is 3 minus 1. So now we got to do the math. 3 to the third is 27. 3 squared is 9 times 6, that's 54. 9 times 3 is 27 plus 1. And let's distribute the negative sign to everything on the right. So it's negative 1 plus 6 minus 9 minus 1, all divided by 2. 27 plus 27 is 54, and that cancels with the negative 54. 1 minus 1 is 0, so that cancels. And then 6 minus 9 is negative 3. Negative 3 minus 1 is negative 4. Negative 4 divided by 2 is negative 2. So the average velocity in these 2 seconds is minus 2. Now what about the instantaneous velocity at t equals 2? So we found the average velocity between a time period of 1 and 3 seconds. What about at 2 seconds? What is the instantaneous velocity? To find it, we need to use the function that we have for the instantaneous velocity, which is 3t squared minus 12t plus 9. That's what we had in the last example. So we simply have to plug in 2. So it's going to be 3 times 2 squared minus 12 times 2 plus 9. 2 squared is 4 times 3, that's 12. 12 times 2 is 24. 12 minus 24 is negative 12. If you add 9 to it, then you'll get 3. So this is the instantaneous velocity at t equals 2, but it's negative 3 though. So let's not forget that negative sign. Now what about the instantaneous speed at t equals 2? What is that equal to? The instantaneous speed is going to be equal to positive 3. Speed is always positive, velocity is negative. So if the instantaneous velocity at t equals 2 is negative 3, the instantaneous speed at t equals 2 is positive 3. Now here's another question for you. How can we estimate the instantaneous velocity at t equals 2 using the average velocity? Notice that the average velocity is not too far away from the instantaneous velocity. If you wish to approximate the instantaneous velocity, you need to choose 2 points where the time at the instantaneous velocity is the midpoint of those 2 points. Notice that 2 is the midpoint of 1 and 3. But 1 and 3 is not too close to 2. So the answer is not the same. It's a little bit off, but it's still pretty close. So pick 2 numbers where 2 is the midpoint of those 2 numbers, and those 2 numbers are very close to 2. A good example would be 1.9 and 2.1. 2 is the midpoint of 1.9 and 2.1. If you add 1.9 and 2.1 divided by 2, if you find the average, you'll get 2. So if we find the average velocity between 1.9 and 2.1, it should be very close to the instantaneous velocity at t equals 2. So let's go ahead and prove that. Now we're going to use the same formula as we use for average velocity. So it's going to be s of b minus s of a over b minus a, or s of 2.1 minus s of 1.9. That's the change in position, which is displacement, divided by the change in time, which is 2.1 minus 1.9. So if you plug in 2.1 into s of t, you should get 2.701. At least that's what I got. And if you plug in 1.9 into s of t, you should get 3.299 divided by 2.1 minus 1.9, which is 0.2. And if you type this in your calculator, you'll see that the average velocity is negative 2.99. Notice that the average velocity is a good approximation of the instantaneous velocity. So make sure you're familiar with this, because you might need to use that technique for data tables. Now, how can we know when the particle is moving to the right, when it's moving to the left, and when it's at rest? What would you do to find the time intervals for each of those situations? So the first thing you need to do is find the velocity function, which we know it's 3t squared minus 12t plus 9. Remember, when the velocity is positive, it's moving to the right. And when it's negative, the particle is moving to the left. And if it's at 0, it's at rest. So let's set it equal to 0 and let's solve for t. So we need to factor the GCF, which is 3. 3t squared divided by 3 is t squared. Negative 12t divided by 3 is negative 4t. And 9 divided by 3 is 3. So now we need to factor this trinomial. Notice that the leading coefficient is 1. In this case, find 2 numbers that multiply to 3, but that add to the middle coefficient of negative 4. This is going to be negative 1 and negative 3. Negative 1 times negative 3 is positive 3, but negative 1 plus negative 3 adds up to negative 4. So to factor it, it's going to be t minus 1 and t minus 3. So to solve for t, we need to set each factor equal to 0, because if one of them equals 0, the entire right side is 0. 0 times anything is 0. So for the first one, we need to add 1 to both sides. And for the second one, we need to add 3 to both sides. So therefore, t is equal to positive 1 and positive 3. So if you plug in 1 or 3 into the equation, v of 1 is 0 and v of 3 is 0. So the particle is at rest at t equals 1 and t equals 3. Now it's temporarily at rest. It's going to change direction because the particle is moving at these times. Now we want to find out when it's moving to the right and when it's moving to the left. To do that, we need to create a number line. So once you make the number line, you want to plug in points to see if the velocity is positive or negative. It might be easier to plug it into factored form. So let's use this part of the equation. So if we plug in a number that's greater than 3, let's say 4, is the velocity going to be positive or negative? So if you plug it into t in the factored form, it's going to be 4 minus 1 times 4 minus 3. Now 4 minus 1 is a positive number, and 4 minus 3 is a positive number too. A positive number times a positive number will give you a positive result. So to the right of 3, it's positive. Now what about between 1 and 3? Let's say if we plug in 2. 2 minus 1 is positive, and 2 minus 3 is negative. A positive number multiplied by a negative number will give you a negative result. Now what if we plug in a number less than 1, let's say 0.5. 0.5 minus 1 is a negative number, 0.5 minus 3 is negative. Two negative numbers multiplied to each other will give you a positive number. Now, when is the particle moving to the right? What is the answer in interval notation? So using a number line, wherever it's positive, it's moving to the right. So it's moving to the right when t is greater than 3 and when t is less than 1. Now we need to know what are the bounds on the left and on the right. Now if this was a regular function without any restrictions, all the way to the left would be negative infinity, and to the right it would be positive infinity. So the answer would be negative infinity to 1 union 3 to 1. That's when it's moving to the right. However, this is not a function where x can be anything. This is a function with respect to time, and time starts at 0. So we can't go to the left of 0, so it can't be negative. Now granted, time can go to infinity. However, the original function was restricted from 0 to 5. If we didn't have this restriction, the domain, or the particle, would be moving to the right from 0 to 1 union 3 to infinity if we didn't have this restriction. But since we do have it, it's moving to the right from 0 to 1 union 3 to 5. So that's the answer for this particular problem. Now here's another question for you. Why should the answer contain brackets at 0 and 5, but at 1 and 3 we have parentheses? Why is that the case? What do you think the reason for that is? So here's a question for you. What is the velocity at 0? If you plug in 0 into this equation, what number will you get? It's going to be positive 9. 3 times 0 squared minus 12 times 0, that's 0, plus 9, which is 9. Now remember, the particle is moving to the right when the velocity is positive. So at t equals 0, at exactly 0, it is positive. So that's why it includes 0. Now, what if we plug in 5? What is v of 5? If you plug in 5, it might be easier to use this form. It's going to be 3 times 5 minus 1, which is 4, times 5 minus 3, which is 2. 2 times 4 is 8 times 3, that's positive 24. So at 5, the velocity is positive. So it's moving to the right, so it includes 5. If it includes the answer, use brackets. Now what about 1 and 3? So if we plug in 1 into the velocity equation, what number do we get? So if we plug in 1, 1 minus 1 is 0, so the whole thing is 0. So at exactly 1, the velocity is not positive or negative. So it's not moving to the right when t is exactly 1. That's why it doesn't include 1, so we use an open circle or a parentheses. The same is true for 3. If you plug in v of 3, 3 minus 3 is 0. So it's not moving to the right or to the left at t equals 3. So we need a parentheses because it's an open circle at these 2 points. Now, when is the particle moving to the left? How would you write your answer using interval notation? The particle is moving to the left in this region, between 1 and 3. So it's simply 1 to 3, but it does not include 1 and 3, because v of 1 is not negative and v of 3 is 0, it's not negative. So only when the velocity is negative is the particle moving to the left. So it's from 1 to 3 using parentheses. Now, how can we find the intervals when the velocity of the particle is increasing and when it's decreasing? So we need to find when acceleration is positive and when it's negative. So we have the velocity function with respect to time. It's 3t squared minus 12t plus 9. So using this equation, we need to find the acceleration. The acceleration is the derivative of the velocity function. The derivative of 3t squared is 6t, and the derivative of negative 12t is minus 12. Now let's set the acceleration equal to 0, and let's see when it's positive and when it's negative. If we factor out a 6, we could see that the acceleration is 0 at t equals 2. So now we need a number line. Now we know the graph, or this entire problem, is bounded from 0 to 5. Now if we pick a number between 2 and 5, is the acceleration positive or negative? Let's say if we plug in 3. 3 minus 2 is positive. Times 6, that's going to be a positive number. Now if we plug in a number between 0 and 2, like 1, 1 minus 2 is a negative number. So it's going to be negative in this region. Therefore, we could say that the velocity is increasing when acceleration is positive. So it's increasing on the interval 2 to 5. Now 5 is included, but 2 is not. And here's why. If you plug in 2 into the equation, what is the instantaneous acceleration at t equals 2? Plugging in 2, 2 minus 2 is 0, so the whole thing is 0. So the acceleration is not positive at 2. Therefore, it does not include 2, so we have a parentheses at 2. So the velocity is not increasing at 2 since the acceleration is 0. In fact, when the acceleration is 0, the velocity is constant. So it's constant at t equals 2. Now what about at 5? What is the acceleration at t equals 5? If you plug in 5 into this equation, 5 minus 2 is 3 times 6 is 18. So it's a positive number. So the acceleration is positive at t equals 5. Therefore, the velocity is still increasing. So 5 is included in the interval. So that's why we're using brackets. Now what about when the velocity is decreasing? The velocity is decreasing whenever the acceleration is negative. So it's decreasing from 0 to 2. Now it doesn't include 2 since it's not negative at 2, it's 0. But it does include 0 because the acceleration at 0 is a negative number. If you plug in 0 into this equation, 0 minus 2 is negative 2 times 6. You get a negative number, which is 12. So the velocity is decreasing at t equals 0. Here's the next question for you. At what interval is the particle speeding up and when is it slowing down? So if you remember, the particle is speeding up when the acceleration and velocity have the same sign, and it's slowing down when they have different signs. So let's combine the two intervals that we have for velocity and acceleration. The number line that we had for velocity looked like this. The critical numbers were 1 and 3. So to the left of 1, it was positive. Between 1 and 3 was negative. And between 3 and 5, it's positive. But let's put the endpoints, 0 and 5. Now for acceleration, the only critical point that we had was at 2. Now we still have the endpoints 0 and 5. To the left of 2, it was negative, and to the right, it was positive. Now what we want to do is we want to combine these two number lines into a single number line. So we're going to have the critical points 1, 2, and 3, and also the endpoints 5 and 0. So I'm going to put the velocity on top and the acceleration on the bottom. So between 0 and 1, the velocity is positive. Now between 1 and 3, it's negative. So it's negative between 1 and 2 and 2 and 3. And between 3 and 5, it's positive. Now let's move on to acceleration. Acceleration is negative between 0 and 2. So between 0 and 1 and 2, it's negative. Between 2 and 5 is positive, which corresponds to 2 to 3 and 3 to 5. Now with this combined number line, when is it speeding up and when is the particle slowing down? Now remember, it's speeding up when acceleration and velocity have the same sign. So that's between 1 and 2 and 3 and 5. So we can write it like this, 1 to 2, and then union 3 to 5. Now 5 is included. Now, should we include 1, 2, and 3, or some of those points? So at t equals 1, is it speeding up, or is it at rest, or is it constant? What's going on? Now remember, if velocity is 0, and if acceleration is positive or negative, that means it's speeding up. If the acceleration is positive, the velocity is about to increase. It's about to go from 1, 2, 3 to 4. So it's about to speed up. It's moving away from 0. If the acceleration is negative, the velocity would decrease to negative 1, negative 2, negative 3, negative 4, which the speed is still positive. So the speed is going from 0, 1, 2, 3, and 4, even though the velocity is becoming more negative. So either way, if the velocity is 0 and if the acceleration is positive or negative, the speed is about to increase. So it's speeding up. Now the velocity is 0 at 1 and 3. So therefore, at those 2 points, if we want to be very technical, we can put a bracket, because it's about to speed up at those 2 points. Now what about when it's slowing down? The speed is decreasing whenever the velocity and acceleration have opposite signs. So that's between 0 and 1 and 2 and 3. Now it includes 0. We know that at t equals 0, the acceleration is still negative and the velocity is positive. So 0 is included. 1 is not included. At 1, it's actually speeding up. It's not slowing down. At 1, the velocity is currently 0. And if the acceleration is positive, the velocity is increasing. If the acceleration is negative, the velocity is decreasing, but the speed is increasing, because if velocity is negative, speed is positive. So no matter what, when velocity is 0, if acceleration is positive or negative, it's speeding up, not slowing down. Now between 3 and 5, or rather 2 and 3, it's also speeding up. But it doesn't include 2 or 3. Now, I meant to say that it's slowing down between 2 and 3. I think I said it's speeding up, but it's actually slowing down between 2 and 3. So I want to make sure I mention that. Now, when is the particle moving with constant speed? The speed is constant when the acceleration is 0, just as the velocity is constant when the acceleration is 0. And the acceleration is 0 at exactly t equals 2. So at t equals 2, the particle is moving with constant speed. Now, why is it that when the acceleration and velocity have the same sign, it's speeding up, and when their signs are different, it's slowing down? Let's understand why that's the case. So first, let's see what happens when they have the same sign, when they're both positive. Now let's say the acceleration is 5. It's a constant 5. What is the velocity at t equals 1? Let's say if initially the velocity and the speed is 0. So 1 second later, the velocity is going to be 5. 2 seconds later, it's 10. 3 seconds later, it's 15. So as you can see, when the acceleration is positive, velocity is increasing. The acceleration is the rate of change of velocity. So if the acceleration is 5 meters per second squared, that means that the velocity is increasing by 5 meters per second every second. Speed is the absolute value of velocity. I'm using s as speed and not as position. So the speed and velocity will have the same magnitude. So as you can see, the speed is increasing as well. So it's speeding up. Now let's see what happens if acceleration and velocity are both negative. So this time the acceleration will be a constant -5. And let's say the particle starts from rest. 1 second later, the velocity will be -5. 2 seconds later, -10. 3 seconds, -15. So as you can see, when the acceleration is negative, velocity is decreasing. On a number line, -10 is less than -5. So as you go this way on a number line, the value is decreasing. So that's why we could say velocity is decreasing. Now what about the speed? If velocity is -5, the speed is +5. And if velocity is -10, the speed is +10. And here it's going to be +15. So even though the velocity is decreasing, the speed is still increasing. So as you can see, whenever acceleration and velocity have the same sign, the speed is increasing. Now let's say if acceleration is positive and if velocity is negative. Let's see what's going to happen in this case. So let's say the acceleration is a +7 and it's a constant 7. Now let's say it doesn't vary with time. It's always 7. Now let's say the velocity initially is 0. 1 second later, actually, we can't choose 0. We need to choose a negative number. Let's say it's -35. It has to be negative. So the acceleration is positive, and whenever the acceleration is positive, velocity is increasing. So right now, the particle is moving to the left, but the acceleration vector is towards the right. So 1 second later, the velocity is going to increase by 7. So if you add negative 35 plus, if you add 7 to negative 35, you're going to get negative 28. If you add another 7, negative 21. So every second, the velocity will increase by positive 7. Now the speed is positive 35. Since the velocity is negative 35, speed is always positive. Now, 1 second later, it's going to be positive 28, positive 21, 14, and 7. So notice that the velocity is increasing. Negative 7 is to the right of negative 35 on a number line. So that's why we could say v is increasing. But if you notice, the speed is decreasing. 7 is to the left of positive 35 on a number line. So it's slowing down. So if you plot this data on a number line, notice what's going to happen. So looking at velocity, initially it's at negative 35, and eventually it goes to negative 7. So the velocity is increasing. As you move to the right on a number line, the values are increasing. Now, in the case of speed, it started at positive 35, but it decreased to positive 7. 35 is to the right of positive 7 on a number line, so the speed, it's going down, it's decreasing. So as we can see, if acceleration and velocity have opposite signs, it's slowing down. But because acceleration is positive, the velocity is increasing. Now let's go over the last case, where acceleration is negative and velocity is positive. So this time, let's say the acceleration is negative 10, and it's constant. And let's say velocity is a positive number. Let's say it's 50. That means the speed is 50. 1 second later, it's going to be 40. If the acceleration is negative, velocity is decreasing. So if you add negative 10 plus 50, you get negative 40. And if you add another negative 10, it's going to be 30, and then 20, and then 10. Every second, the velocity is going to decrease by 10. Now, if velocity is positive, speed is positive. So the speed is also decreasing. So the velocity is decreasing and it's slowing down. So as you can see, the particle will be slowing down whenever acceleration and velocity have opposite signs. Now, how can we find the displacement of the particle during the first 5 seconds? What would you do to find the answer? To find the displacement is simply the change in position. It's s of b minus s of a, or simply s of 5 minus s of 0. It's the change in position during those 5 seconds. Now remember, the position function is t to the third minus 6t squared plus 9t plus 1. So let's go ahead and calculate it. So s of 5, let's plug in 5 into the equation. So it's 5 to the third minus 6 times 5 squared plus 9 times 5 plus 1. And then minus s of 0. 0 to the third is 0. Negative 6 times 0 is still 0. And 9 times 0 is 0 plus 1. So we can cancel the 1's. 5 to the third is 125. 5 squared, that's 5 times 5, which is 25 times 6. 6 quarters, that's basically $1.50, so 6 times 25 is 150. 9 and 5 is 45. And then 125 minus 150, that's negative 25 plus 45. So the displacement is negative 25 plus 45, which is the same as 45 minus 25, so it's 20. So this is the displacement, or the change in position, that the particle moves in the first 5 seconds. So that's how you can calculate displacement. is simply the final position minus the initial position. Now, how can we find the total distance that the object travels in the first 5 seconds? How can we do that? So feel free to pause the video as you work on this example. Now, what you need in order to find the total distance is you need to know the time when the particle changes direction. And what was those times? The particle changes direction when the velocity is 0, which occurred at t equals 1 and t equals 3. Now you want to find the total distance on the interval from 0 to 5 in the first 5 seconds. So what you want to do is you want to calculate the position at the two endpoints at t equals 0 and t equals 5, and also you want to find a position when it changes direction, that's at 1 and at 3. So we know that if we plug in 0 into the function, everything is 0, so it's going to be 1. If we plug in 1 into the function, it's going to be 1 minus 6 plus 9 plus 1. 1 minus 6 is negative 5, 9 plus 1 is 10, negative 5 plus 10 is 5. So we simply get 5 at position 1. Now what about at position 3? If we plug in 3, it's 3 to the third minus 6 times 3 squared plus 9 times 3 plus 1. 3 to the third, that's 3 times 3 times 3, which is 27. 3 squared is 9 times 6, that's 54. 9 times 3 is 27, and then plus 1. 27 and 27 is 54, which cancels with the negative 54, so we just get 1. Now, for position 5, let's plug in 5. We know that 5 cubed, which is 5 times 5 times 5, that's 125. 6 times 5 squared is 150. 9 and 5 is 45 plus 1. So 125 minus 150 is negative 25. Plus 45, that's positive 20. Plus 1, that's 21. So that is the position at t equals 5. So now how can we use this to find the total distance? Well, let's make a number line. So at t equals 0, we started at position 1. And then 1 second later, we ended at position 5. So in the first second, the particle traveled from position 1 to position 5. So it moved 4 meters to the right. That's the displacement for the first second, from 0 to 1. Now, from 1 to 3 in the next 2 seconds, the particle traveled 4 meters back to the left. It might be feet, could be yards, but we're going to use meters. So the displacement is negative 4. Now, between t equals 3 and t equals 5, it changes direction again. It goes to position 21. So it travels from position 1 to position 21. So if you do 21 minus 1, that's a change or a displacement of 20. Now notice that you can use this to calculate the overall displacement in the first 5 seconds. If you simply add the individual displacements the way they are, you're going to get the net displacement. So if you add positive 4 plus negative 4, they cancel and give you 0, plus 20. That gives you the overall displacement in the first 5 seconds, which we calculated when we did S of B minus S of A. S of 5 minus S of 0, 21 minus 1 gave us a net displacement of 20. So you can calculate the displacement both ways. Now what about the total distance? What is the total distance traveled? Now remember, distance is scalar, it's always positive. In the first second, it traveled a distance of 4. In the second second, or in the next 2 seconds, it also traveled a distance of 4. From 1 to 3, the displacement is -4, but the distance traveled is +4. So any negative numbers that you see in this particular instance, make it positive if you wish to calculate the total distance. So we have 4 plus 4, and this is +20. So the total distance traveled is 28. And so that's how you can find the total distance traveled by an object. That's all you need to do. Now let's say if you have a data table with time and position. And let's say you have the following values. What is the average velocity in the first 2 seconds? How would you calculate the average velocity of the particle in the first 2 seconds? What would you do? So to find the average velocity, it's simply the change in position divided by the change in time. It's displacement over time. So it's S of B minus S of A over B minus A, or S of 2 minus S of 0 over 2 minus 0. S of 2 is 11.7, and S of 0, that's 5, divided by 2. So 11.7 minus 5, that's 11 minus 5 is 6, so you get 6.7. Divided by 2, that's 3.35. So that is the average velocity in the first 2 seconds. Now from this table, how can you calculate, or how can you approximate the instantaneous velocity at t equals 3? The only way to do that is to find the average velocity at 2 points. So you want to pick 2 points where 3 is the midpoint of those 2 points. 3 is the midpoint between 2 and 4 and 1 and 5. But 2 and 4 is closer to 3 than 1 and 5 is. So we need to use 2 and 3. So the instantaneous velocity at 3 is approximately equal to the average velocity, which is going to be S of 4 minus S of 2 over 4 minus 2. So now, let's calculate what this is equal to. So S of 4 is 12.6, S of 2 is 11.7. So we have 12.6 minus 11.7, and 4 minus 2 is 2. 12.6 minus 11.7, that's basically about 0.9 divided by 2, which is equal to 0.45. So the instantaneous velocity at t equals 3 is approximately 0.45. So if you have a position versus time function, the velocity represents the slope of the tangent line, and the slope of the secant line is the average velocity. Now what if we have a data table that contains time and velocity as opposed to time and position? And let's say we have these values. Go ahead and calculate the average velocity, not the average velocity, but the average acceleration in between t equals 2 and t equals 5. So the average acceleration is the slope of the secant line for the velocity time graph. So it's going to be S of B minus S of A, or S of 5 minus S of 2. Not S, but it has to be V instead of S. So V of 5 minus V of 2 divided by 5 minus 2. So basically, you're using a slope equation. we're using y2 minus y1 divided by x2 minus x1. It's the change in y over the change in x. The velocity is associated with the y variable, and time is usually plotted on the x-axis. So you're just finding the slope of the secant line. The velocity at 5 is 38.1, and the velocity at 2 is 28.4 divided by 3. So this time, let's use a calculator. 38.1 minus 28.4, that's about 9.7. And if you divide it by 3, you should get 3.23. So that is the average acceleration between t equals 2 and t equals 5. Now, how can you approximate or estimate the instantaneous acceleration at t equals 4? So if you want to find the instantaneous acceleration at 4, calculate the average acceleration between 3 and 5, where 4 is the midpoint of 3 and 5. So a of 4 is approximately equal to v of 5 minus v of 3 over 5 minus 3. The velocity at 5 is 38.1, and at 3 it's 36.1 divided by 2. So 38 minus 36 is 2. 2 over 2 is 1. So the average acceleration between 3 and 5 is 1. So we can approximate that the instantaneous acceleration is approximately 1. It may not be the exact answer, but that's the closest that we can get to, given the data that we have. Now, for some of you out there, you may have to find the velocity and the acceleration using the limits or the definition of the derivative. So if you have to do that on a test, this section is for you. Let's say the position function is t cubed. Calculate the velocity function with respect to time using the limit process, and also find the velocity at t equals 2, which is the slope of the tangent line at t equals 2. So first, let's do it the easy way. We know that the derivative of t to the third is 3t squared. And the velocity at 2, you just got to plug in 2 into this equation. 2 squared is 4 times 3, that's 12. So let's put this here. Now let's use the limit process to get these answers. So if you want to find the velocity with respect to time, use this equation. F prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x divided by h. So in this case, the velocity, which is the derivative of the position function, that's s prime of t, that's going to be equal to the limit as h approaches 0 for the function s of t plus h minus s of t divided by h. So this is equal to the limit as h approaches 0. S of t plus h, we got to replace t with t plus h. So it's going to be t plus h raised to the third power. And s of t is simply t to the third, and then divided by h. The only issue is I need more space. There's not enough space in this board. So let's move this over here. Now you can FOIL t plus h 3 times, or you can factor it. using the difference of perfect cubes equation. So a cubed minus b cubed is a minus b times a squared plus ab plus b squared. So we have the limit as h approaches 0. Now you need to realize that a is t plus h and b is t. So it's a minus b, or t plus h, which is a, minus t, which is b. A squared is going to be t plus h squared. And then a times b, that's t plus h times t. And then b squared is simply t squared. And this is all divided by h. So t minus t cancels. So what we now have is the limit as h approaches 0, h times all of this stuff divided by h. So these two cancel. And so now we have this expression. Once you cancel the h on the bottom, you can now replace every h with 0. So the limit as, well, once you plug in 0, you don't need to write the limit anymore, so we're done with that. So right now it's t plus 0 squared plus t plus 0 times t plus t squared. That's what we now have. T plus 0 is simply t, so that's t squared. This is t times t, so another t squared, plus another t squared. So 1t squared plus 1t squared plus 1t squared, 1 plus 1 is 3. So we get 3t squared, which is the same as this answer. So that's how you can use limits to find the derivative of a function. In this case, the velocity function from the position function. But now, how can you find the velocity at a point? How can you use limits to get this number? To get that number, you want to use the alternative form of the derivative, which is this equation. F prime of a is equal to the limit as x approaches a for the function f of x minus f of a over x minus a. So in this case, instead of f of x, this is really going to be s of t, and this is s of a over t minus a. So we can adjust the formula. So we could say v of 2, which is the same as s prime of 2, that's the limit as t approaches 2 for the function s of t minus s of 2 divided by t minus 2. So now let's plug in what we have. Let's get rid of this. That's taking up space. Let's move this somewhere over here. So this is all equal to the limit as t approaches 2. Now s of t, we can replace it with t to the third. And then minus s of 2. So if we plug in 2 into this equation, it's going to be 2 to the third, which is equal to 8, divided by t minus 2. So now how would you simplify this particular expression? What would you do? Notice that you can factor using the difference of cubes method as we did in the last example. So a cubed minus b cubed, that's t cubed minus 8. And we know it's equal to a minus b, which is t minus 2. If a to the third is t to the third, then a equals t. If b to the third is 8, then b equals 2, because 2 to the third is 8. So you got to find the cube root of 8, which is 2. And then it's a squared, or t squared, plus ab, or plus 2t, plus b squared, which is 2 squared, and that's 4, divided by t minus 2. So notice that the t minus 2 variables, they cancel. And notice what we have left over. So we have the limit as t approaches 2, t squared plus 2t plus 4. Before, we couldn't plug in 2 because 2 minus 2 is 0, and it would be undefined. But once we eliminate the t minus 2, we can now replace 2 with 0, so we don't have to rewrite the limit function. So it's going to be 2 squared plus 2 times 2 plus 4. 2 squared is 4, 2 times 2 is 4, plus the other 4. If you add 4 3 times, it's the same as multiplying 4 by 3, and you get 12, which is the slope of the tangent line, or the instantaneous velocity at t equals 2. So that's how you can calculate it using the limit process. You need to use the alternative form of the derivative, and it's going to give you the velocity at a certain point, rather than getting the velocity as a function. So this is it for this video. Hopefully you found it to be educational. So thanks for watching, and do well on your next calculus exam.